Good. So last time, we started to look on this random feature model where we have to multiply our data matrix with random weights, and then we also want to take a nonlinear function on the entries. And the question is whether we also can calculate the eigenvalue distribution of f times f transpose. And the idea was somehow to use this Stein's identity and see whether we have an extension of this to a situation where our random variables are neither Gaussian nor independent, and this was a cumulant expansion. And I gave last time some idea how this works, and we saw that we have to introduce objects which we call cumulants, which were defined by an analytic definition. You take the logarithm of the characteristic function, and the coefficients there you call cumulants, and we also saw that we have a kind of extension of Stein's identity in this situation. Okay, but today I want to talk a bit more systematic about those cumulants. Maybe start again and define them and give all their main properties, because they are very important objects in general, but also in particular in our case. And we have to be able to calculate cumulants of products, for example. So we have to see how to do this. So I want to make a short intermezzo where I talk about cumulants and their properties and uses. Okay. And so we defined them in analytic way, but last time I already showed you that there is a kind of diagrammatic or combinatorial interpretation where you have you define them in terms of moments, and this is given by summing over all partitions. And so maybe let me be more precise on this. So really define maybe precisely what is a partition. So this is a partition of a set, not a partition of a number. In number theory, you often have partitions of numbers, but here we have really partitions of sets. So this is just a decomposition of my set into non-empty disjoint subsets which generate the same set. And usually I denote this by pi. So pi is a collection of subsets, V1 up to Vr. So this is a partition, pi, partition of a given set. Let me call this S. So S is given. For example, usually S will be the numbers 1 up to n, but it can be an arbitrary set. So if what? So if the VI's, of course, they should be subsets of S, and they should be not empty. So all of them are non-empty subsets. Then they should be disjoint. So Vi and Vj. Intersection is the empty set whenever I is different from j, and together they should just give the whole set. So the union of them is just everything. So V1, union V2, union, and so on, up to, I have here R of them. So this is S. So I write S as a disjoint union of subsets. Okay, so that's a very general notion of a partition. And the V's, usually I call the blocks of the partition. So we'll call in this case, V1 up to Vr, the blocks of pi. Yeah, okay. And then maybe I also write, in principle, you can say such a partition gives me an equivalence relation by decomposing my set into equivalence classes. So I'm not sure whether I will use this in the following, but maybe it's good also to have this. So if I have two elements in my set, let's say P and Q in S, then I say they are equivalent, of course, with respect to the given pi, if P and Q are just in the same set V, in the same block. If P and Q belong to the same block of pi. Okay. And of course, if I have an equivalence relation on my block S, I mean the equivalence classes are just blocks of a partition. So partition and equivalence relation on such a pi is more or less the same. Good. Okay, then maybe I use the notation that I call, I'm looking on all partitions of a given set, and I call this P of S. So the set of all partitions of S is denoted by P of S, P for partitions. And usually this set S are just, let's say, the numbers 1 up to n, and then I write just Pn. So it's a short form. So Pn, this is just the partitions of the set of the numbers 1, 2 up to n. Yeah, good. Okay, so that's abstract notation, but I mean very often I use this graphical notation, so I just can draw the partitions. So often we use a diagrammatic representation of partition pi. So for example, I mean, let's say I take a partition of 5 elements. So I have 5 elements, 1, 2, 3, 4, 5. Okay, and then let's say as a partition, let's say I take a partition which has, let's say, 2 blocks. So the first block consists of 1 and 3, and the second block consists of 2, 4, and 5. Okay, then this partition tells me that 1 and 3 belong together. They are in the same block. So I draw this like this. Okay, and 2, 4, and 5 are also connected. They also belong to a block. 2, 4, and 5 also belong to a block. Okay, I mean here I have a crossing between the 2 blocks, but the 2 blocks don't belong together. So I also always do it like this. So I mean here those belong together, but here not. Okay. Okay, so but here I'm not going to distinguish between crossing and non-crossing. So all partitions are good. Okay, maybe another one is if 2 and 3 belong together, and 1 and 4 belong together, and 5 is on its own. So this would be the partition where one block is given by 1 and 4, another block is given by 2 and 3, and one block is given by 5. Okay, and I usually, if I write things down, I mean those are sets. I mean 1 and 4, and 4 and 1 is the same, but usually I order them in increasing orders. So usually, I mean, I have an order. I mean, I can, I mean the set S doesn't need to have an order, but usually I have an order, and so I order my numbers, but it doesn't really play a role for this. Good. Okay, maybe one should also see that in principle I can put an order, a partial order, on my partitions, namely if I get one partition from another one by splitting a block or several blocks into smaller blocks, then what I get should be smaller. And in this sense, there's a largest partition and there's a smallest partition. So maybe let me maybe let me just write it down in this example. So I mean the smallest partition, of course, is the one where I have decomposed it in as many blocks as possible, which means every element is its individual block. So it's this where I just have singletons. So this I would denote by, so this is the smallest one, so this is 0, and so 0n in general, but here it would be 0, 5, but because it's 5 elements. Okay, and the largest one, of course, is the one which contains as few blocks as possible, so namely just one block where everything is connected. So I have here just I call it 1, 5. Okay, so this is the smallest element in P of 5, and this here is the largest element in P5. Good. Okay, so that's my definition of partition. And now what we want to do is we want to use those partitions to define cumulants. Okay, and so cumulants in a multivariate setting. So I mean I have variables, a collection of random variables, and usually let's say I consider them as an algebra. So I mean I have maybe my random variables in which I'm interested. So maybe I have a random vector, and then I have the components, which might be independent or might be not, might be Gaussian or not. So I have a collection of random variables. But then, of course, if I'm looking on moments, I also multiply them. And usually I can also take the sum. So I take the algebra generated by them, and I want to define moments and cumulants on this object. So I mean, in the following, so usually I have an algebra, so A. So this is an algebra of random variables, which I consider. So for example, if I have a collection of random variables in which I'm interested, then I take all polynomials in them. So all things which I can get by multiplying them by real or complex numbers, adding them and multiplying them. Okay, yeah. And then of course on this algebra I have my expectation. I can take an expectation of sums and products of my random variables. That's essentially, if I take monomials, products of my random variables, that's the moments. That's the main information which I have about my objects. And now we want to rewrite this in some other quantities which we call cumulants. Okay, so what we are given is essentially this pair. I have my algebra of random variables, and I can take the expectation. I just take the expectation of elements from here. Elements from here are usually products of maybe my basic random variables. Okay, so this means if I have this, we know all moments. And moments are just expectations applied to elements in my algebra A. Good, okay. But we can now rewrite this and into some objects, and those we call cumulants. And this is given by a formula which I already essentially indicated last time, that namely the moments are given by summation over partitions. But for this also we need a kind of multiplicative extension of these moments. And let me do this in the following notation. So namely in this sum, I will have I sum over partitions, and each partition is not one cumulant, but it's a product of cumulants. Or maybe if I do it the other way around, I'm not just looking on moments, but I'm looking on products of moments. And the product structure is according to the blocks of a given partition. So if I have a partition pi, which consists of blocks V1 up to VR, let's say a partition of n elements, and I have, let's say, n random variables, t1 up to tn in A, then I take now a moment of those random variables, but not just a moment where I multiply all of them, but I multiply only the ones which are in each block of the given partition, and take then the expectation of this and multiply them. So this means I take now, which I denote by e pi, so I'm putting the pi here, of the t1 up to tn. So this is now not just one moment, but it's a product of moments, where for each block of pi I have a, so for each block v in pi, okay, this is the product sign and this is my partition. So I have a moment E where I take the t's which correspond to this block. Okay, so maybe let me, so this here, I mean this is just the expectation of the elements which are sitting at a position which are given by my block. So this is just ET1, ET2 up to TIS if my block V, so I mean this is a block of a partition of 1 up to n, so it's a subset of 1 to n, so it has some numbers and I order them, because essentially I mean I want to keep the order which I have here. I mean, my random variables commute, so the order is not really important, but maybe it's better to really have them in one order and also take the products in this order. So I have here the V is E1, which is less than E2, and so on, which is less than IS. So just the numbers I1 up to IS in this block, and I have ordered them in increasing way. And then I multiply the variables which are sitting at those positions. Okay, so that's just a notation. So this is a product of moments according to the blocks. Good. Okay, and then we will also have the other quantities which we call cumulants, and for them we also use this kind of notation so that we can also multiply cumulants according to a given partition. So I do now essentially the same for cumulants. And the cumulants, okay, I still have to define what they are, but if I have them, then I also do this extension with the pi. So let me say how I do the extension if they are given. So if you have a collection of, and I call them kappa n, where n is running to the natural numbers, and actually the cumulants are kind of more, somehow more complicated objects than the moments. I mean, the moments are just, this is just the linear function applied to elements here. The kappas, they get an index n, and each kappa n is an n linear functional. Okay, so it takes n arguments, and I have to distinguish the arguments. So actually, I will have those kappa n's. So these are n linear functionals. So this means each kappa n takes not only one argument from A, but n of them. So it goes from A to the n to, let's say, R. And so if I plugging in n elements from my algebra, I'm getting the kappa n, T1, T2, up to Tn. Okay, and so suppose those guys are given, and I'm going to define them, but if I have those guys, then I can extend those kappa n's also to objects where I put as an index a pi, an arbitrary partition. And I'm doing this in a multiplicative way. So given this, we extend this in a multiplicative way as before. To all p of n. So namely, I define now a kappa pi. And again, so if, let's say, if pi is in Pn, I again have n arguments, T1 up to Tn. But now, this is not just one kappa, but it's a product of kappa and one kappa for each of the blocks. So it's a product of the blocks of pi. And then I take the kappa, which has the index here as the size of this block, and that the t's which I put there are exactly the t's which are connected by my block V. So I'm taking here again not all the t's, but only the t's restricted to V, which has the same meaning as before. So this here, this is a kappa. And I mean, kappa has a number here telling me how many arguments I take, and I take as many arguments as the block V has number of elements, and then I take here just the kappas of T of I1, T of I2, up to T of I, let's say S, and then I mean this here is S. If the V is I1, I2 up to IS, as before. So I mean here I'm just multiplying things, and I don't need to put commas, but here I have to put commas because it's just a linear thing. Good. Okay. So this means if I and of course I mean the original kappa n in this language of, let's say, T1 up to n. This, of course, is kappa of the largest partition, 1n. So this fits together, because then I just take, I only have one block here. So the product is actually just one one block, which is everything, and then I'm just back to the kappa n. So in a sense, I mean, this here, the kappa pi is an extension of the original thing, namely if pi is equal to 1 n, then I'm back to here, but I have extended it in a multiplicative way. Okay, so this is essentially just notation, but now I can define the cumulants, and yeah, also the definition is a bit indirect, because I'm defining them in implicit way, not saying explicitly what is the nth cumulant if I'm giving the moments, but I'm giving a relation between moments and cumulants, which essentially tells me how to calculate the moments out of the cumulants. But this is an equation which can be solved in a recursive way, and we will look on examples. But maybe let me give the definition in this direction, because this is the simplest formula which we have. Okay, so we are given our setting that we have the algebra of our random variables where we have an expectation, so we can take moments, and then we define corresponding cumulants of the random variables in our algebra of the random variables in A. Yeah, we define this by defining now the kappa n's. So the kappa n's should be multilinear functionals from a n to r. So each kappa n should take n arguments and random variables, and then it should spit out some number. Okay, and how is it defined? By a relation between moments and cumulants, and usually I call those relations a moment-cumulant formula, because it relates moments and cumulants. So this is defined by the moment-cumulant formulas. So I mean we have them for all n in n, and all possible choices of random variables which I plug in those guys. Okay, so here's the formula. So it tells me what the expectation of this moment is corresponding to this, where I'm just multiplying this. So I take the nth moment of those random variables, and I mean the t's, I mean they could be the same or they could be different. I mean it's just elements from here. So all the t's could be the same, but it could also be different. And some of them could be the same, some of them different. So it's just, I just denote them in general by t1 up to tn. And I'm looking then on the product of t1 up to tn, taking the expectation. And this can be written in the cumulants by this formula, which is a combinatorial formula. So I'm summing over all partitions of n. So n is the number of factors which I have here, and then each pi gives me a contribution, and the contribution is exactly this kappa pi. So I have here kappa pi of t1, t2 up to tn. Okay, so this means, I mean, yeah, the kappa n's, if the kappa n's are defined, the kappa pi's are also defined according to the above, but this relation here should define me those objects. Okay, and maybe I call this moment-cumulant formula. Good. Okay, and yeah, the point is really to see that this is really a definition, because I mean, if we would know the kappas, then this would define the e's, but of course we know the e's, we know the moments, and it should define the kappas. So we should see that this is really something which we can solve for the kappas. And so let us do this in the following by looking on examples. Of course, we have this for all n, so we can look on it for small n and then go higher and higher and see that in each step we get new information about the nth cumulant. Okay, so let us look on examples. So the smallest possible n, of course, is n equal to 1. And so what does this equation tell us in this case? Yeah, n equal to 1. And of course, for n equal to 1, I only have a t1, and p1 is of course just the partitions of the set consisting of one element. And of course, there's only one partition, because I cannot decompose this in any way. So there's just one block. So if So if I have 1 point, and maybe I can also put the T1 there, and then of course the only partition is just taking this block. And then of course this tells me that E of T1 I have to sum over, just this element. So I get a contribution from this element, and what is the contribution? I should take the kappa corresponding to a block of size 1, so I have a kappa 1, and then I put just the argument there. And so this just tells me that kappa 1 is nothing else than the expectation. So kappa 1 is the expectation or the mean. Okay, so I mean, in this sense, kappa 1 contains already all the same information as E. Okay, so that we introduce more kappas is that we reorganize things in a meaningful way. Okay, but anyhow, so this means if I solve this, of course, it tells me that kappa 1 of T1 is equal to E of T1, and I can define kappa 1 in this way. Good, okay, now more interesting, of course, n equal to 2. Okay, there I have, of course, 2 points corresponding to T1 and T2, and now there are 2 partitions. I can either take those 2 guys together, or I can take them separately. And this gives me 2 summands in my moment-cumulant formula. So this means the expectation of T1, T2. So the contribution corresponding to this, so there's only 1 block, so I should take a kappa corresponding to this block. This block contains 2 elements, so it's a kappa 2, and I put there the 2 variables which are in this block, kappa 1 and kappa 2. But then I also get a contribution from here. So this is a product of 2 kappas. Each of them has only 1 argument. So it's a kappa 1 of the first block, which contains the T1, multiplied with the kappa 1 of the second block, which contains the T2. Okay, and now you see this tells me what kappa 2 is, because I already know what kappa 1 is. So I can solve this for kappa 2, T1, T2. This is equal to the expectation of T1 times T2, and then minus kappa 1 of T1 times kappa 1 of T2. But of course the kappa 1s are just the expectations. So this is the same as E of T1, T2 minus E of T1 times E of T2. Okay, and so now this is now, I mean, how this, I can now use this for defining kappa 2, or that's what my definition is telling me concretely. And you see also this is something which we usually know in the random matrix context. So this is the covariance of the 2 variables T1 and T2. So this is a meaningful object. So this was a mean, this is the covariance, and now we also have higher ones which somehow play a higher order role, like mean and covariance. Okay, and maybe let me also write down 3. Okay, so this was for n equal to 3. So there, what do I have there? There I have, let me write it, maybe let me write it here. So I have the expectation of T1, T2, and T3. And I should sum over all partitions of 3 elements. Let me draw the picture here. So I have T1, T2, and T3. And now there are actually 5 partitions of those guys. I can take all of them together in 1 block, or I can take 2 of them together. One is staying alone, or all of them are staying alone. So that's the 5 possibilities which I have. Nothing more and nothing less. And each of them gives me a contribution here. So the first one, of course, there's 1 block. So I have a kappa 3, where all the arguments are in this kappa 3. And then I have 3 terms where I have a kappa 2 times a kappa 1. So here I'm taking together T1 and T2, and then multiply it with T3. By the next, I take together T1 and T3, multiply it with T2, and then by this one, I have 2 and 3 together in 1 block, 2 and 3, and 1 is alone. And in the last one, I just have 3 blocks, which each containing 1 variable. So it's just a product of 3 kappa 1s, kappa 1 of T1 times kappa 1 of T2 times kappa 1 of T3. Okay, and you see now again, I can solve this for kappa 3, and the other terms only contain kappa 1 and kappa 2, and I already know what they are in terms of the expectation. So I can solve this. So this tells me kappa 3 of T1, T2, and T3 is actually this expectation. So essentially, I mean, the kappa, the nth kappa is essentially the nth moment, but then I'm getting correction from lower order moments, which, okay, maybe at the moment it's not clear. What are they good for, those corrections? It looks like a complicated definition. So of course, this should have some value, and I will tell you about this value, but at the moment, at least there's a clear structure behind this formula. So a very combinatorial one. So we have this, and then I have to subtract all those other guys. So I have to subtract kappa 2, T1, T2 times kappa 1, T3, and so on. But of course, I can express this in terms of the expectation. So this is the expectation of T1 times T2 minus the expectation of T1 times the expectation of T2. And this here, of course, also, so this is the covariance of this, and this is the mean. So this is the expectation of T3. So each of those terms I can write in expectations, because they are smaller order cumulants, which I already knew from before. Okay, and then I can multiply this out and collect terms, and in the end I get a formula which is very similar to this formula here, namely, let me write it down. Yeah, so what you see essentially, you get terms which again correspond to pies, to partitions. Yeah, so namely, what do I get? Of course, I first get this term, E of T1, T2, T3. Then I'm subtracting the terms where I have here T1 and T2 together times T3. So I have terms like the expectation of T1, T2 times T3. And then I get, of course, corresponding terms corresponding where I take T1 and T3 and where I take T2 and T3 together. So minus E of T1, T3, E of T2 minus E of T2, T3 times E of T1. And then, of course, I also get the terms where I have products. So I mean, here I also have E1, T1, ET2, ET3, the product of the three terms, but I also get it from here. So this term I get more often. And sometimes I get it, let me see, I mean, here I get it with a plus, but from each of those terms I get it with a minus. So I have it 3 times with a minus, once with a plus. So in total, I get this 2 times with a plus. So plus 2 times, let me see, is it plus? Plus. Okay, I mean, this goes on the other side. This gives me a minus, and those here actually give me a plus, because I have a minus here and a minus here. So I have 3 times with a plus, once with a minus, so I get in total plus 2 times E of T1, E of T2, E of T3. And now you see I'm summing here again according to the 5 partitions of 3 elements. So what I have here is the expectation where I have this partition. I only have 1 block. Here I'm subtracting where 1 and 2 are together, 3 is alone. Here I'm subtracting, I have 1 and 3, 2 is alone. Here I have E to the 1 is alone, 2 and 3 are together. And here I have 2 times the expectation of where I have 3 blocks of all arguments. So you see, I can solve this relation, saying that the expectation is given by summing over all partitions, and then I just get this multiplicative contribution of the cumulants. I can solve this, and I get then a very similar formula. I can say the cumulant is given by summing over all partitions, and I get this multiplicative contribution of the moments, but now I get also some factors. You see I have here minus, and I also have here 2. So it's not that I always get just a coefficient plus 1, but I get more complicated coefficients. But the structure of the formula is again the same. And this is in general. So I mean, this was here observed for 3, but this is true in general. And so what we are doing here is essentially a kind of inclusion-exclusion principle. I mean, we are bringing terms on the other side, but then you see, I mean, this here also gives smaller order terms which we have to collect, and so we do a kind of inclusion-exclusion principle, or more general, this is called a Möbius inversion. What we are doing here is a Möbius inversion on this poset which we consider here, on this partially ordered set. So this just means I can solve an equation of this type for the guys here, and I get an equation of the same type, but I get more complicated coefficients here. And the coefficients which I get here on this side are usually called the Möbius function of what I have here. Okay, but anyhow, it's not so important. I mean, I can write it down explicitly in this case. So maybe let me do this in the next theorem. So I'm not going to prove it, but I mean, this can be done, and I mean, in this example you see it. I mean, here you see those coefficients are the Möbius function of the poset which I consider here. Yeah, so let me write it maybe here. So it's changing the moment-cumulant formula into the Cumulant-moment formula, where I express cumulants in terms of moments. The structure is the same, only the coefficients are getting a bit more complicated, but still are manageable. So let me formulate it as a theorem. Essentially, it's about solving this equation here for the kappas. Okay, so this definition here, which was a kind of recursive definition, or an implicit definition, not giving the kappas explicitly, but only with an equation. So the recursive definition of the cumulants via the moment-cumulant formula is equivalent to the explicit formula, Cumulant-moment formula. So namely, I can really write down a formula which expresses the nth cumulant in terms of the moments. And this formula is as before. I have to sum over all partitions of n elements, and then each of them gives me this multiplicative form of the moment. So it's just the product of moments according to the blocks of pi. So it's e pi of all the variables which I have, t1 up to tn. But then I get a factor, and this factor abstractly is the Möbius function of this situation, but concretely it's going with a sign. So it's -1 to the number of pi -1. So it's a number of blocks in pi, and then I also have a factorial, namely the same as here, so the number of pi -1 factorial. And so you see so you see that here, I mean, this fits here, so I have the minus sign. So if the number of blocks is even, then this is negative, this is odd, then I have a -1. And so I mean here are the three situations where I have number of blocks are 2, there I get a minus sign. For the other cases I get a plus, and then the last term, the number of blocks is 3. Okay, so I get the plus sign here, but here I get 3 minus 1 factorial, so I get a 2 factorial, which is this 2. Okay, so this fits with this. Good. Okay, so that's the moment. Let me call it that's the cumulant moment formula in this situation. And I have this here very explicitly. Okay, but very often the explicit value is not so important. It's more to understand the structure of the formula and being able to see some more structure there. if you apply it to specific situations. I mean, of course, this formula is quite horrible. I mean, if you really want to use it explicitly, I mean, you're summing over all partitions, and if n is getting a little bit bigger, I mean, there are so many that you cannot really, I mean, you cannot really do anything with it. So, I mean, it's really that at some point you have to do a summation in analytic way, collecting terms together. Okay, but I mean, in between, maybe you want to argue that some terms vanish or so, and for this it's very good to have this combinatorial characterization. Good, okay, but of course I should tell you why do I introduce those objects. I mean, at the moment they are just defined, and of course they should have something to do with the problems which we have at hand. So in particular, they should have something to do with random variables and check whether they are independent or not. Because usually what we have in our situation, we are starting from some independent random variables. And those cumulants are very good for checking independence. That's the main property. That's why they are introduced. So independence, of course, is defined in terms of moments. You can say, I mean, random variables are independent if expectation of a product of them factorizes. Okay, so this should now be rewritten in terms of a property of the cumulants. And this property is the vanishing of mixed cumulants in independent random variables. Okay, so this was here 712, maybe the central theorem about the relevance of cumulants, why they are really useful. So let us consider the setting that I have an algebra of random variables with their expectation, and then I consider their subsets of random variables, and I want to know whether those random variables are independent or not. So consider here subsets, and let me call them Ti, subsets of A for some indexing set. Could just be a set of 2. So I just have some random variables in T1 and some in T2, and I want to know whether they are independent. Okay, it could just be that I have one random variable here in T1 and one in T2, and I just want to know whether those two random variables are independent. So those are my random variables, and the claim is this can be decided in terms of the cumulants. So then the following are equivalent. So namely, first, the fact that the Ti's are independent, which by definition is something in terms of the moments. We know the factorization of moments, but what does it mean for the cumulants? For the cumulants, it means that mixed cumulants in the Ti vanish. So this means many of the cumulants are 0, namely whenever I have a cumulants, and then the entries are either coming from one of the Ti's, but if if at least 2 of the Ti sets are appearing both in the cumulant, then it is equal to 0. So this means that kappa n of T1 up to Tn is equal to 0 whenever, I mean, each of the arguments here should be coming from one of the sets which I consider. So let's say it should be from the set Tij, but it should also happen that at least 2 different from those sets are showing up. So I should have here random variables coming from at least 2 of those guys. So this means I have here a mixed cumulant because the arguments are coming from 2 different sets. So I mean, each of them comes from one of the set, but at least 2 different sets are showing up. So I have at least position L and K such that JL, the T set which I have at the position L, is different from the T set which I have at the position K. Good. Okay, and so let me make this clear and maybe also give a proof of maybe one direction, maybe the one which is most interesting for us. Namely, if I have the vanishing of these mixed cumulants, that this really means that those guys are independent, which means I have the factorization. So I mean, the vanishing of mixed cumulants is equivalent to the factorization for the random variables. And I mean, this direction is maybe the easier one, but it's also the other way around. This is really a characterization. But so maybe let me give the proof, or just maybe example of a proof, and only this direction, that vanishing of mixed cumulants implies factorization of moments. And so for this, let us consider, maybe just to be specific, consider a moment, and let me just take two of these t sets, and the elements in one of them I call little t, in the other I call little s. So I have t random variables and I have s random variables, and the t's are independent from the s. And I look now on a mixed moment in them. So let's say I look on t1, s1, t2, s2, s3, t3, t4, something like this. So, and I assume this condition 2, so I assume that mixed cumulants in the t's and the s's vanish. Where mixed cumulants in the two sets, I mean, the sets are now T1 would be the set which consists of the T's, so this is T1, T2, T3, T4, and the other set, T2, is the set which consists of the S's, S1, S2, S3. Okay, and so I'm saying if I have a cumulant where I have both T's and S entries, then this is equal to 0. That's the vanishing of the mixed cumulants. And what I have to see on the moments is that such a product factorizes. I mean, this should factorize, of course, I mean, everything commutes, so this is T1 times T2 times T3 times T4 times S1, S2, S3, and then this should factorize into the moment of the product of the T's times the expectation of the product of the S's. That would be the independence of those guys from these guys. Then it factorizes, and I mean, I should see this now from this formula. Okay, yeah, so those guys were mixed cumulants in this vanish. And now we should see the factorization of the moments following from this. So I should calculate the expectation of this product T1, S1, T2, S2, S3, T3, T4 by using my moment-cumulant formula. So I should sum over all partitions of 1, 2, 3, 4, 5, 6, 7 elements, and each of them gives me a contribution, and the contribution is a product of cumulants according to the blocks. Okay, and so if I have now a block of pi which connects a t with an s, for example, if I would have a partition like this, I mean, those are partitions which are showing up in this sum here. Okay, but this would have a block, so this block here contains both t and s, and by my assumption this is equal to 0. So this means in my sum here, such partitions don't make a contribution. Okay, so this here is not allowed. I mean, it is allowed, but it will make the contribution 0. So maybe the kappa pi of this is equal to 0. Okay, so this means I only have to sum over partitions where each block only contains either s's, only s's, or only t's. And so this means any partition which I have decomposes into, it has some blocks which connect the s's, and it has some blocks which connect the t's. So essentially I have a partition of the s positions, and I have a partition of the t position. So I mean, for example, something like this, where I have here this one, maybe this s here could go with this s, and I could have this. So this would be okay. So I mean, here's a block which only has two t1s, the t's, and here I have the t's. So this block and this block on its own make up a partition of the positions where the t's are, and then I have here other blocks which only connect S. Here S1, S3, and here an S2. So this is okay. This would be okay. The kappa of this would make a contribution, but here I can say the pi, the partition of all positions, decomposes into a partition of the positions where the S are. So if I call this pi S, and a partition of the positions where the t's are. And of course the kappa of this here, so this is the product of the kappas corresponding to the blocks here. I mean, this is of course the kappa given by taking the product over those blocks times the kappas taking the product over those blocks. So if the pi decomposes like this, then the kappa of pi also decomposes as the kappa of pi s times the kappa of pi t, and where I'm distributing the arguments, of course, accordingly. I mean, here I only get s as arguments, and here I only get t's. Okay, and so this means that my sum here, which a priori is a sum over all partitions, and I get this contribution kappa pi, that this actually is a sum where I only have to consider pi's which factorize into blocks which only contain S and blocks which only contain T. And then what I get here, this argument, or this contribution also factorizes into the product of the kappas corresponding to the blocks of pi S times the kappas corresponding to the blocks of pi T. But then you see I'm summing here over those guys, and I'm summing over those independently. I mean, the blocks which I choose for the T positions, I can choose them arbitrarily, independent of the blocks which I'm choosing for the S position. So I'm just choosing all possibilities for the blocks at the T positions and all possibilities for the blocks of the S position, and I can combine them in an arbitrary way. So this sum here is actually just a product of the sum over all possibilities here times the sum over all possibilities here. So this here is then the sum over all pi s, and I have the kappa pi s, and here of course I only have the s arguments sitting at this position times the sum over all pi t, and I have here the kappa pi t of all the t variables. But I mean now I have here the same problem as before, namely I sum over all cumulants at all possible partitions for those positions here, and then this here gives me just the expectation of the product of the s's which I have here. This is now just again the moment-cumulant formula, but only applied to the positions where the s's are sitting. So this here is the expectation of all the s's. So in this case this would be expectation of S1, S2, S3, and this here is the expectation of the product of all the t's. So this would be T1 times T2 times T3 times T4. And so you see I get the factorization of the product as I need it for the independence. And so the vanishing of the mixed cumulants gives me the factorization of the moments. Okay, and one can also go the other way around. Anyhow, but maybe at least this gives you the main idea how this is connected. Good, so maybe a few remarks on this. Maybe first of all, I already said it, that of course here everything commutes. So if I have a cumulant of T1 up to Tn, I can permute the t's and it's still the same, because I have here commuting variables. So in the moments everything commutes. So if I commute here things, I can also commute here things, and the structure of this formula goes over to itself. So those cumulants, even though I write things in a specific order, because it's somehow nicer for the structure of the formula, everything is commutative. So of course, I mean, instead of writing this in this form, I could bring all the t's at the beginning and all the s at the end. And then I also should have the factorization. But I can also keep it in this order. Yeah, but on the other side, I mean, if I bring all the t's at the beginning and all the s at the end, then of course here on this side I also have the same, that in my arguments for the cumulants I have all the t's at the beginning and all the s at the end. If I don't do this, then I have the arguments are somehow mixed between t's and s. But it's all the same. So note that cumulants do not change under permutations of the arguments. So for example, I mean, just for example, I mean, kappa 3 of T1, T2, T3 is the same as kappa 3 of T1, comma T2, T3, T2, or maybe it's the same as kappa of T3, T1, T2, etc. Yeah, because this I mean, this formula also goes into each other. I mean, so I mean, the contribution which is showing up here is also showing up here. Maybe not for the same partition, but the partitions are mapped onto each other under such permutations that all the contributions showing up here are also showing up here. Good. Okay, but so maybe a more important remark or question is, so I mean, why the heck am I doing this very complicated thing? I mean, the cumulants are quite complicated. I mean, these formulas here, they have some nice structure, but still I'm calculating cumulants in a quite complicated way. And even the vanishing of mixed cumulants doesn't seem to be so much better than the independence, which is just a factorization of moments. So why do I really want to introduce those objects? So they have something to do with independence, so they should be useful, but are they really much more useful than moments, for example? Is it really worth to introduce them? And maybe, yeah, so the answer to this, of course, we will see that they are useful, but maybe a general answer is that actually if I'm doing expansions around special situations, in particular situations containing independent Gaussians, then they are somehow easier to deal with in this formulation. Okay, and maybe more concretely, in a sense, is, I mean, factorizations. Okay, if you have factorizations, this is the same as having vanishing of mixed cumulants. But if you have approximations, then maybe you don't have factorizations, you only have approximate factorizations, and this corresponds to having approximate vanishing of cumulants. And usually it's easier if you do estimates to see that you have small terms instead of seeing that you have terms which factorize almost. So it's easier just to work with this. I mean, it's better to have almost vanishing or smallness of cumulants than having almost factorizations of moments. That's maybe a general one. But of course, we have to see later in concrete applications that it's quite useful to have those cumulants. Okay, so why are cumulants good objects? Or maybe better in some cases, of course, in some cases better than moments. Yeah, because, yeah, let's say almost vanishing of cumulants trumps, yeah, maybe almost factorizations of moments is better than almost factorization of moments. Good. Okay, but of course, cumulants are linear objects. Moments are also linear objects. But of course, we also have our algebra of variables, and of course, we multiply our random variables. I mean, moments are usually products of random variables. And for the cumulants, so in order to really deal with them, we have somehow to be able to calculate cumulants of products of random variables if we know the cumulants of the individual random variables. Okay, on the level of moments, I mean, taking a product is not a big deal. I mean, if you multiply things, you just have a moment. Okay, but if you multiply random variables for cumulants, you're changing somehow. You take cumulants of other objects and you must connect them. And so what we really need to be able to make a good use of cumulants is that we understand how the product goes with those cumulants. And maybe that's the next thing, and maybe the last thing in this general setting which I want to talk about, because this will be important if we go back to our random feature model, because there we are multiplying two of our random matrices, and each of them is very nice, so we understand their cumulants, but the question is, do we understand the cumulants of the product of W times X, of the weight matrix and the data matrix? And for this we need to understand what happens if I multiply random variables in the arguments of my cumulant. Let us first, for the moments, it's essentially just associativity. So, moments are in a sense associative. So, if I multiply a few things, it doesn't matter where I put brackets. And putting brackets corresponds somehow to putting the commas in the cumulants. So, if I would say, let's say I take a second order moment of, let's say, T1 times T2 times T3. So I have three variables, but now I say, okay, the first two I multiply, so this would be my new variable, and this is another one, then this would be a second moment. But of course, this is the same. I don't need the bracket here. I can also say this is the third moment of T1, T2, T3, or I can also say it's the same as the second moment of, if I multiply here T1 with T2, T3. Okay, so putting bracket doesn't really make a difference here, and I can move my variables around here. On the level of the cumulants, I cannot do this. So if I would like to do the same for the cumulants, let's say I take the cumulant, the second cumulant, where the first argument is T1, T2, and the second argument is T3. So is this the same as if I move this T2 over here? So I can calculate this. So what is this? The second cumulant is the covariance. So it's the expectation of the product of T1, T2 with T3. And then I'm subtracting the product of the two means. So of the first variable, which is T1, T2, times the mean of the second variable, which is here T3. And of course, I can do the same for T1, comma T2, T3, where if now I'm not multiplying T1 and T2, but I'm multiplying T2 and T3, and consider this second cumulant. This again is the covariance, so it's T1 times T2, T3, and here of course this is the same, because in leading order moments and cumulants are the same. It's just the subleading orders which make corrections, but in the subleading orders, of course, this comma here matters. So namely, this is now the expectation of T1 times the expectation of T2, T3. And this term is not the same as this term. So this means those guys here, in general, are not the same. So one has to be careful. And the question is now, this is not true, but is anything true? Can I deal with, or can I control cumulants where I have here products? In particular, can I control it in terms of cumulants where I take all the variables individually? And indeed, there's a formula like this. So namely, let us look on the, let's say, kappa 2, T1, T2, comma T3. So as I wrote it above, okay, let me write it again. So this is the expectation of T1, T2, T3, and I'm subtracting the expectation of T1, T2 times the expectation of T3. Okay, and now of course I can write all this in terms of cumulants. So I want to have a formula which expresses me the cumulant of this situation in terms of cumulants of all the variables T1, T2, T3. And of course all this I can express, so namely here I know that by the moment-cumulant formula I can express this by cumulants by summing over all the partitions of 3 elements. So I'm summing over terms corresponding to those 5, okay, let me do 5 situations. So I get here those 5 terms. Okay, and here I also get terms, and some of them are the same as here. So namely, so some of them are going away. So namely here I get, I mean, for this I get 2 possibilities. Namely, I can connect it. For this I only always get this possibility, or it can be disconnected, which corresponds to this term. So you see that of the 5 terms here, 3 are subtracted. So I get here a formula which expresses this as a sum over now only 3 terms, and those are really given in the usual form that I take a product of cumulants according to the blocks. So this means that this here actually is, what remains is this term, kappa 3 of T1, T2, T3. This is gone away. This here survives, plus kappa 1, T1 times kappa 2, T2, T3. And this one here also survives, plus kappa 2, T1, T3 times kappa 2 of T2. Is this okay? No, kappa 1. No. Good. Okay, and now of course the question is, I mean, okay, so here I have a nice formula saying I'm getting a sum over some partitions, but do we understand the structure of what we really get here? And actually, there is a structure behind here. So namely the 3 terms which I have here, the 3 partitions which make a contribution, are the ones which somehow connect the group of T1, T2 with the group of T3. So you see, I mean, here T1 and T2 somehow belong together. They are multiplied together. They are already connected, but T3 is not connected essentially, and so I have to sum over all possibilities where I'm connecting those groups. So you see here, I mean here this is connected to T3, but here you see there's no connection between this group and this group. So I only have a connection within this group, but not to this. Then here again, this T3 is connected to this group via T2, and here it is also connected. But here everything is separated, so there's no connection here. Okay, so the reason, and the ones which are separated, they are subtracted away because they are also appearing here. Okay, and this is true in general. So namely, what I have here is a formula where I can express this here in cumulants of my individual t's by summing over all pi's which are connecting exactly those groups. And this is true in more generality. So I mean, I can also, okay, I can have bigger cumulants, and in each argument I can have a product of cumulants. And so maybe that's the basic theorem about the multiplicative structure about cumulants. So consider n random variables and multiply them together in groups. Multiply them together in, let's say, m groups. So this means, I mean, I have variables, so I call them T1, little t1, up to Tn. I have n of them. I mean, some of them can be the same, some of them can be different, but I just give different names to them. And then, so I'm looking on T1 up to, and then I'm multiplying the first, let's say, I1 together. So I multiply those, and I call this capital T1. Okay, then I have the next one, which is Ti1 plus 1, and I again take a few up to I2, and I multiply them together. I call this T2, and so on, until the last group. And for the last one, this goes up to the last one, starting somewhere here, and I call this Tm. Yeah, of course there can also only be one factor in those groups. I mean, here the T1 would be T1, T2, and the capital T2 would be T3, where nothing is multiplied. But in general, I can multiply for each argument. I can multiply as many guys as I want. Okay, and then the point is that we can now express the m's cumulant of the capital T's, so T1, T2, up to Tm. So each argument here is now a product of some of the little t's. And I can write this as a sum over kappa pi's, where here I take the cumulants of the little t's. So I have here T1, comma, T2, comma, and so on, comma, Tn. And I'm summing here over pi. Okay, pi in principle must be a partition of n elements. So P is in Pn. But I'm not summing over all of them, but only over some of them, and those should have the property that they connect the groups which correspond to the capital T's. So here I have a condition such that pi connects all the capital T groups together. Okay, I mean this can be written more formally, but I hope it's clear in this pictorial. I mean there must be ways of going via blocks from each T to some of the other T's. Okay, but I mean which of the little T's I'm using for doing the connection, it doesn't matter. I mean here I have a situation, I mean here I must connect this group with this group, and I can do this via the T2, but I can also do it via the T1. I can also do it by both, but it's enough to have one of the guys here which is connected. Good. Okay, so that's the general formula, which is also, okay, maybe not totally straightforward, but it's also not so hard to prove it by using the moment-cumulant formulas. Or maybe I should say we can check some of the extreme cases that they are correct, because we know that they coincide with things which are either trivial or which is the moment-cumulant formula. Okay, so the extreme cases, maybe which we should consider as an example, is where I don't multiply anything together, or where I just multiply everything together. Okay, so maybe let us first look on the case where I don't have any product. Examples. So the first case is no products. So I have as many capital T's as I have little t's, and the capital T is just the corresponding little t. So because I mean there is no product involved, and so what does this formula tell me then? So it says that I have kappa n of the capital T's are now just the little t, so I have T1 up to Tn on this side, and now I'm saying this is the same as the sum over all partitions of n elements where I have this extra condition, and then I take kappa pi of T1, T2 up to Tn. So now it looks as I'm expressing a kappa n as a sum of other kappas, but now we should think about what is this condition here. This condition tells me that all the groups should be connected, but the groups are now just these single guys, and so I must connect them all, and there's only one partition which connects them all, which is the one partition. So I need a partition which really connects them. Okay, so this condition here means that pi must be equal to 1n. And then the kappa of this guy is just the kappa n. So this here is just the same as kappa n of T1 up to Tn, because in this sum there's only one pi which makes a contribution. Okay, so it's just says kappa n is equal to kappa n. Good. Okay, but now maybe the other extreme, where I only have one product. So I'm multiplying all my arguments together, which means I only have one capital T. So I only have one T, which is the product of T1, T2 up to Tn. Okay, and then the m is equal to 1, and then on the left-hand side I have kappa 1 of T. And this, the formula now tells me that this is given by the sum over pi in Pn with some condition here, and I have here the kappa pi of T1 up to Tn. But now what is now the condition? I mean I have to connect all the groups in the capital T's, but there's only one capital T, so there is no condition at all, because I mean they are already connected. I mean this T is just this product. I don't have to connect it to anything else, so I can forget about this. So I'm really summing over all of them, and if I sum over all kappas, over all cumulants, kappa pi's, I just get the moment. I just get the expectation of T1 up to Tn. But this is okay, this is consistent, because I have here the kappa 1 of T, and we know that the kappa 1 is the same as the expectation. So this is E of T, and T is this product. So you see that this is consistent. Yeah, and in principle, in this case, we can see directly that the formula is true. But of course, those are the trivial extreme situations, and the formula will be used in intermediate situations where we multiply a few things together. So maybe a last example is that if we do kappa 3, and maybe now I'm multiplying the first two together, and then I have two more, T3 and T4. So I'm just multiplying the first two together. So I have a capital T1, this is the product of those two. Then I have a capital T2, which is this guy, and a capital T3, which is this guy. And then what is the formula telling here? So I can express this in kappas of the individual T1, T2, T3, T4, where I'm summing over all partitions which have to connect, I mean this group here, with the other guys. So this means those guys here must be connected with T1 and T2. This can of course be achieved if I connect everything, and if I'm not connecting everything, then yeah, I mean the T3 must be okay. Yeah, there are many possibilities. I think I have forgotten here a couple of them. Let me see. So I mean, I still can have both connected, and they can connect. No. Okay. I mean, if they are both connected, then they must connect like this. Okay. If they are not connected, then one of them must connect to one of them, and the other must connect to the other one. So I mean, it could be that T2 connects to T3, but then T1 must connect to T4. So I mean, then T3 is connected to this group, and T4 is connected. It could be that T1 connects to T4, no, to T3, and T2 connects to T4. Yeah, or it could be that one of them connects to the other two, and the other one is alone. So T1 could be alone, but T2 makes a connection to the other two, or T2 is alone, and T1 connects to the other ones. So, okay, I think that's all of them, unless you see some more. And then, of course, you get in a formula, you get the contributions. So I mean, this would be kappa 4 of T1, comma T2, comma T3, comma T4. This here would be a product of kappa 2s. So a kappa 2 which has T1 and T4 as an argument, and a kappa 2 which has T2 and T3 as an argument, and so on, for each of those terms. Good. Okay. Yeah. So maybe I leave it with this. You can work it out. But you see, I mean, if you really want to write down all terms, in particular, if you want to write down a bit more complicated example, where you really multiply a few things here, a few things here, and a few things here, you will really get a lot of terms. And usually you prefer not to write them down. So you know the structure of the formula, and usually you want to use this in some arguments for maybe getting some results that some cumulants vanish, or maybe you can connect one cumulant with other cumulants. Okay, but usually, okay, it's not that having this really explicitly is what you really want. It's more the structure which is there, which you can use in arguments. And so hopefully next time we are going back to this random feature model, and then we in particular have to look what are the cumulants of the entries of our F matrix, where the entries are given by taking products of entries from each of the two matrices. So each of the two matrices is a standard Gauss. So in each matrix, the entries are Gauss and independent, but then I start to multiply them. And then with this formula, I will be able to say something about the structure of the cumulants which I get there. Good, okay, but that's yeah, for next time. So that's it for today. Thanks.